Okay guys, in this video, so we already started the substitution of the e, ikx, and e to the negative alpha k squared t, where k is an integer. So we've done the left side derivation, which is this. So now we're going to do the right side, which you're taking the derivative twice. So for the first part, the alpha e to the k squared t alpha multiplied by I squared k squared e to the I kx. And we know I squared is equal to -1. So as we move this down, this is going to be equal to e to the alpha. This should be negative up here. Say -1. Alpha k squared t times e to the I kx times negative alpha. And if you look at this, there should be a negative there. These are the same. So it means, let's go back up. This ikx times e to the negative k squared t is the solution for this. You're taking a temperature for a count of position and a second derivative of temperature for a count of position. It's a solution not accounting for the boundaries. So that is an important target. It's not accounting for the boundaries. So that's what the stability is for this. And we're also going to have to do a Newman's analysis on this. So let's just say Newman's. So Newman's stability. So we used a finite difference equation that we obtained earlier. So at some position j at a later time is equal to at some position j, same node, at an earlier time plus r, in which r is negative alpha, change in time with respect to position squared. So r times at some position to the right at an earlier time minus at some position, so 2 at some position, j, same position at an earlier time, plus t at some position to the left at an earlier time. And what we know is e to the negative alpha k squared t e to the negative I kx determines the stability of the equation. And when we do this for tjn, we'll get tjn is equal to the same thing, k squared j x times e alpha negative k squared in t. We're in here, so the n here is our time increment, and the j here is our spatial increment. And these x's and t's are delta, so they're changing. So as we substitute these values back into the full equation shown here, we should get tj plus 1 is equal to 1, so that's the original tjn, plus r e to the negative, this is positive, so kx minus e to the negative ikx. Might be plus, let's say plus for now. I forgot the minus 2 in the middle. So that's minus 2. And this one is for the left side, and this is for the right. So what we know is, from Euler's equation, e to the ikx is equal to cosine k to x plus I sine kx k delta x. And we know cosine's an even function, sine's an odd function. We substitute these, so Euler's equation back in, and we'll get TJN plus 1 is equal to 1 plus R cosine k delta x minus 1. So that is where we are now. And what we know from the stability equation is, when it gets bigger than 1, it's going to go to infinity and negative infinity. So this value actually has to be smaller. So this value here, got off a draw. This value here is smaller than 1. But we're going to take the absolute value of this. So it's going to be now, the absolute value is going to be less than negative, greater than negative 1. It's R cosine k to x minus 1 and greater than 1. So we're going to subtract 1 from each side. So you have this same equation now, 2 and 0. Bring that down. I'm not going to waste the time drawing it. And what we know from cosine, well, this is one. Cosine functions, their intervals are from negative 1 to 1. And we know this is less than 0. So now we divide the function by negative 2. Or divide the function by 2. We'll get there 1. It's greater than R. So we'll just talk about the inside function. Delta x minus 1. And what we know, if we did this to find the smallest possible value for cosine k delta x minus 1. And when we did that, the smallest value you can get for this is negative 2. So what we got to do now is divide the function by negative 2. And we know the smallest value sets the boundary limit so that we can determine stability. So we divide this by 2, change signs when you're dividing by 2, or divided by a negative. We'll get a half. So R is less than a half, which sets the stability. And that is the Newman's stability analysis for this.